Good evening or good afternoon, so whatever. My name is Lalit Mehta. I am a vice president at Path Science. We work in digital pathology space. And I knew Professor G since about 6 years when I was working on MRI scanners in the radiology field. So interestingly, since then we have kept the connections. I used to be an adjunct as well here for 2 years, so in the same department where he works. And I taught AI in cybersecurity, so that was different from what I am doing now. It gives me a great pleasure to introduce Professor G. He's a full professor in the Department of Electrical and Computer and Systems Engineering. He did his PhD in University of Washington, and he holds some leadership positions, like he's the director of Intelligent Systems Lab at RTI, and also he's a fellow of the IEEE and also the International Association of Patent Recognition. That's really a big honor, and he has been in this field for quite some time. He was a program director at National Science Foundation, which is a pretty difficult job, by the way, to run some of those reviews and reach the decision on funding research. And his academic journey is quite prolific. So he has taught at University of Illinois, Urbana-Champaign, then Carnegie Mellon University, and also in University of Nevada. Impressive, actually. So, and also you've done research in Air Force Research Lab. Incredible, I know, achievement he has. About 300 publications, and a lot of students work with him. Some of his students really worked on my projects for MRI scanners. So it's really a thrill, and we're very happy to have Professor G give this talk. And one thing I would like to mention, I am actually a chair of the IEEE Computational Intelligence Society. And this talk is in collaboration with Computer Society. So IEEE is organizing this. So thank you, and pizza will be coming, so you can get up and enjoy pizza as well as listen to the talk. Thank you.
Thank you. Thank you. Thank you for the invitation from IEEE, and I'm very happy to give a presentation about recent research in my group. And so first, I want to show that, as you well know, that AI right now, enabled by deep learning technologies, massive data, and big compute. AI is basically revolutionized almost every field, right? From healthcare, finance, science, to education, manufacturing, and medicine. So it's and it is even hailed as the engine of the fourth industrial revolution. And it is somebody call it the new electricity of the world. So in spite of these hypes, and there are significant fundamental challenges with current AI technology. The first is data intensive. This is because of the data-driven nature of current deep learning models. It requires massive amount of data, a lot of data, and there are annotations to perform well. And the second is the typically lack of trustworthiness and explainability. And they tend to be a black box and cannot explain their prediction very well. And this is because their poor capability in quantifying and explaining its prediction confidence. It also struggles to generalize across domains. So if the model trained on one data set from one domain, it cannot have a good generalization to another domain. Mainly due to the spurious correlation results from various bias in a domain. And these are what we call this. These are the fundamental challenges, and these challenges cannot be addressed by simply scaling up the model, scaling up the data, or scaling up the compute. They require foundational changes in the algorithm. And this is what we try to do, okay? So my group, what we're doing this, we are doing this from the neural-symbolic perspective. Neural-symbolic means that we combine deep learning with the traditional machine learning techniques. And so we are doing this in three areas. The first is what we call the knowledge-augmented deep learning. And here we want to integrate well-established prior knowledge with data to improve the data efficiency of the deep learning model and simultaneously improve the generalization performance. So this is called the knowledge-augmented deep learning. The second is Bayesian deep learning. So we want to leverage Bayesian deep learning to rigorously quantify and quantify, attribute, and mitigate uncertainty, prediction uncertainty, in order to improve model trustworthiness, explainability, and robustness. And thirdly is what we call the causal representation learning. And here we want to combine causal modeling with causal modeling and inference with deep learning, right, to improve model generalization across domain by eliminating the influence of domain biases. So today I'm going to give you a highlight of research in these three areas in my group. First, knowledge-augmented deep learning, right? So the goal here is the ground deep learning in well-established and generic domain knowledge to improve data efficiency and the model generalization. Right? And it consists of two tasks. First is knowledge identification. We need to identify the domain knowledge, generic domain knowledge from different sources. The second is the knowledge integration. So first, let me quickly talk about the knowledge identification. So what is the purpose of knowledge identification? It's to identify knowledge of different types from different sources that govern the property and behavior of the target object that we want to predict. So we are interested in knowledge of different types from different sources, right? So here we are specifically we divide the knowledge into two major categories. The first is a scientific knowledge. So these are the formal theory and laws that govern the behavior and the property of the target object. And they are often precise, quantitative, and they are often represented in mathematical equations. The second is what we call the experiential knowledge. These are the heuristic, insights, rule of thumb, or common sense about the behavior and the property of the target object, and their semantical relationship. And this kind of knowledge typical is imprecise, qualitative, and they are typically expressed in terms of rules, such as logical rules, constraints, symbolic expressions, or graphs, such as knowledge graph. So they are from two different sources, right? They are very different. And knowledge, the prior knowledge is generic. This prior knowledge is generic, well-established, often readily available in a particular domain, and universally applicable to different conditions and settings. And its use can significantly constrain the problem. So the second is the knowledge integration. And the goal here is to incorporate identified knowledge into different stages of deep learning. So now we have knowledge from different sources of different types. We want to incorporate them into different stages of deep learning. So here I show you two stages. The first is the training stage. In the training stage. And here we are going to incorporate the knowledge into the regularization terms of the loss function. So knowledge is injected through the regularization terms of the loss function. So this is the first level. Another is the architecture level. Here we want to design the architecture so that the knowledge can be injected into the model as inductive bias in terms of architecture, in terms of additional layers, additional nodes, modules, or additional pathways. So we want to design the architecture so that the architecture can encode the knowledge. So this is a very quick introduction about the knowledge-augmented deep learning. So now I want to give you a concrete example to show what we're doing. Okay, so now I'll show this in a particular computer vision problem. So the goal here is that we want to do a 3D body mesh reconstruction from images. So the basic idea here is that we have an input image, a body image. The goal is to obtain the 3D body mesh of this body image. And in computer vision, this is typically formulated as a deep regression problem. So you have image, you go through some encoder, you generate the features, and the feature goes through a regressor. This typically is a multi-layer perceptron. And then it output the mesh parameters. This is the pose parameter, and this is the shape parameter, along with the camera parameters. And given the pose and the shape parameters, then go through an analytical function, we'll be able to reconstruct the mesh, right? And then from the mesh, we'll be able to generate the skeleton, 3D skeleton, in terms of the position of the joint angles. Okay, to train this deep regression model, usually we have a loss function. The loss function consists of two terms. The first term is the 2D loss term. Basically, this measures the projection loss. So we have the 3D model, right? We project it to the 2D image. We want to measure the difference between the projection and the observed image. So this is the 2D projection loss. There's also a 3D loss. So this loss measures the difference between the projected estimated mesh parameter and the ground truth mesh parameter, right? However, in order to do this, for this 3D term, we need the motion capture data. We need to capture the motion capture data where we have a ground truth mesh, right? But this motion capture data is very expensive and complex to set up. And also, the motion capture data has a limited diversity in terms of the demographics of the subject and in terms of the body pose, body shape. As a result, if the model trained on one motion capture data, it may not perform well on a different motion capture data. So what we do is that we want to replace this motion capture data term with generic body knowledge from different sources. And then we can replace this motion capture term with a knowledge term, right? So this way, we will not need any motion capture data. So now the question here is, what is the body knowledge? Body knowledge. As if you look online, you will find out the human body has to be studied extensively in many different fields, And here I show you the 4 fields that we use to extract relevant knowledge. First is anthropometry. Anthropometry is about studying about the body parts and their dimensions, right? According to the anthropometry, human body consists of connected body parts. And each body part, the length of each body part is subject to certain proportion. For example, the length of the leg is about 50% of the height. The length of the forearm and the forearm, right, is about is between 1/6 and 1/7 of the body length. So we can come up about 20 body proportions for each body part. And this kind of knowledge is generally valid for most adults. So this is the anthropometry. Another is the biomechanics, body biomechanics. And this is a study of the joint movement. It specifies the degree of freedom for each body joint, right? Not every body joint has 3 degrees of freedom. We would think each body joint should have 3 degrees of freedom, but turn out not every body joint has 3 degrees of freedom. For example, the shoulder joint has 3 degrees of freedom. This elbow joint only have 2 degrees of freedom, and this knee joint only have 1 degree of freedom. So now we can significantly reduce the number of degree of freedom for the joint angles. In addition, there is a range. Each joint angle must move within certain range. And this range is also useful information. So combine degree of freedom with the range for each joint angle that give us additional knowledge. Another is a geometric. There's a geometric constraint on the joint angles. For example, right? These 4 joints, for example, right, tend to be coplanar. They are located on the same plane. While these 3 joints are collinear. So this gives us some geometric constraints on a subset of the joint angles. In addition, we know that the joint of the left part of the body and the joint on the right part of the body are symmetric, right? So this gives us additional information. Finally, we have the body physics. And this here, we use a very simple knowledge, which is the non-penetrating constraint. In other words, the different body parts, when they recover the mesh, the different body parts should not penetrate into another body part, right? So this is called the non-penetrating constraint. So now we have the knowledge from these 4 sources. But what we actually use more than this. But here I just already show you the 4 sources. So now the question here is how can we encode this into the regularization terms of the loss function? Okay, so now I talk about the encoding. So this is basically encoding or integration at the training level, right? So now we have the knowledge. First, anthropometry. And we will be able to construct a term. And this term basically measures the relative difference between predicted body part proportion and the expected body part proportion, right? So to give the relative difference. And then we average this one over 20 body parts. So that give us a one regularization term. And then the body mechanicals. And here we have, for each body joint angle, we have the minimum and the maximum angles, right? So we can put it here, right? So this basically limits the joint angle to the range between the minimum and the maximum. And also, if we set this minimum and the maximum to 0, then this also limits the degrees of freedom. So this constraint both limit the movement of each joint angle as well as the degrees of freedom of each joint angle. And then the geometry. The geometry here we have 2 terms. One is the coplanar. So this term encodes the constraint that the 4 joints on the chest must be coplanar. And this one imposes the constraint that these 3 joints must be collinear, right? So this gives us the geometric constraint. And finally, we have this constraint, the physics constraint. This basically imposes the non-penetrating constraint, right? And here we basically, for any colliding triangle patch, right? Then we measure their distance. And then we minimize their negative distance. In other words, we try to maximize their distance, so that they do not collide with each other. So this is the term, right? So now if we put all this together, we have a knowledge term consists of these 4 regularizations, right? You may think that this seems to be very weak, but if we use them collectively, they form a very powerful constraint on the body mesh that we want to estimate. And then we combine that with the 2D projection loss, right? And then we use this one to train the deep regression model. And here you see the result. So we just here. So we compare with this model, right? This is a human motion recovery model, state of art. It used both 2D and 3D motion capture data. And our model only used 2D plus knowledge. And then we evaluate it on one data set. It is the human 3.6N, right? And if we train and test on the same data set, this is the average joint position errors, right? You can see HMR is slightly better than us, right? Slightly better than us. So we're lower. The accuracy is a little bit lower than this method, right? In this method, in terms of joint position errors. But this method requires motion capture data, and we do not need motion capture data. However, if we apply the model to a different data set, let's say the MPI data set, And you can see the performance is getting much worse for this method. Well, our method is much better than this. The position error is much better. So this shows you that our method does not need any 3D body annotations. We don't need any 3D body annotation, and we achieve comparable within dataset performance, and achieve much better cross dataset performance. It generalizes much better. So this shows you that our model can be very data efficient because we do not need any 3D motion capture data, and simultaneously improve the generalization performance. So yes.
By doing this, how much of
Training data set.
Yeah, because you don't need a lot of training data, right?
Yeah, we do not need the motion capture data. We do not need only motion capture data. We still need 2D data. We do not need motion capture data.
Yeah. So then you save a lot of.
Yeah. So for some data set in the wild, there's no motion capture, and this one still works. But for this method, it needs motion capture data, so it won't work. Okay, so this basically shows you how we can incorporate what we call the experiential knowledge into the deep learning. Now I'll show you another. So this time I'm going to show how the scientific knowledge, the theoretical knowledge, can be incorporated into the deep learning model. The goal here is we want to do physics-informed 3D human body motion estimation and force estimation. Okay, so the goal here is we want to leverage body dynamic theory to improve 3D body motion estimation, accuracy, and physical plausibility. We want to improve motion accuracy and the motion physical plausibility. And also, the output is not limited to 3D body reconstruction and 3D body mesh, but also include forces for each body joint, including the torque for each body joint, as well as contact force. So this is pretty significant. We go from an image to 3D forces for each body joint only, right? So to do this, what we can do? We are going to treat the human body. This is a human body, right? The motion of human body as a what? As a multi-body system of rigid body parts. So the body of a human body dynamics can be captured by the interaction of different body parts, right? And so this is the multi-body system. And this multi-body system is going to, we enforce it satisfy the Euler-Lagrange equation. This is the Euler-Lagrange equation is kind of like the second Newton's law, right? Related the forces and dynamics to the object, right? And it is basically a system of a second order ordinary differential equations, right? And the Q here represent the generalized coordinates of body parts. M is represent the mass for all the body parts, and I are the inertia of body parts. And the Q dot is the velocity, and Q double dot is the acceleration. And this M here is the what we call the generalized mass matrix. It is function for QMI. And this D is called the correlates matrix. It is a force, right? It depends on the velocity of the body parts, as well as the mass and the inertia, right? And on the right side, we have the torque. So the torque here represents the torque of the joint, for each joint, right? And this lambda represents the contact force. So when the joint contact with the external object, there is going to have a contact force. For example, the foot, but when it's contact with the ground, and this is the contact force. And this force is also referred to as the ground reaction force, right? And this J is the Jacobian matrix that maps from the contact space to the generalized coordinate space. So in this equation, right, we need we need a physics parameter. We need M, we need C, we need J. We also need a lambda and tau. These are the physics parameters. Once we have these physics parameters, then this equation is fully satisfied, right? So now I'm going to show you how can we embed this equation into the deep learning model, right? So this is our model, right? So we have for the mesh that the mesh 3D mesh reconstruct from a single image, right? As input, Then we go through a transformer encoder, right? Then from the transformer encoder, it generates the features. And this feature then go to a dynamic regression model, generated the estimation of the forces for each joint, including the contact force and the torque for each joint, right? So this is right. In addition, we have another model called the deformable mice model. This deformable mice model, given the shape of each body part, this deformable mice model allows us to estimate the mice, right? The mice and the inertial for each body part. So once we know the beta, we can fit, so we can get the mass. And once we have the mass and the inertia, then these three matrices are fully specified. This I, M, and C are fully specified. So now, right, if we combine this with this together, then this is the, oh, sorry. Okay. Then this is the Euler, right? The Euler equation here is fully specified. The Euler Lagrange equation is fully specified. So now what we need to do is that we need to solve this equation. We need to solve it. So then we feed this to what? To a decoder. So this decoder is a new ODE solver, neural ODE solver, right? It numerically solves this equation, right? Solve this equation, right? And using this method like a range quota method, right? When it solves this equation, it gives us the Q at time t plus 1, right? And then we compare this solved Q at t plus 1 with the ground truth Q. We will be able to construct a loss term. Then we use this reconstruction loss term to what? To train the model. This way, we can see that the equation here, the Euler Lagrange equation, is systematically embedded into the model, and it is solved by the decoder. So the decoder is not a data-driven, but decoder is what? Is a physics-driven model. So we do not need separate data to train the decoder. And so this is the second, right? We try to inject the knowledge at the architecture level. So by including this physics decoder right here. And now we show you the performance. Okay, so this model is also using transformer. Both is encoder and decoder are transformer, right? And this is ours. That only the encoder is data, but the decoder is the physics, right? So if you compare the reconstruction error, these two methods are comparable. They are not, this one is ours is not much better than this, so we're comparable. But if we compare the physics plausibility, and you're going to see ours is much better than this method, because this method is very data-driven. It did not consider the physics, the underlying dynamics of different body parts. For example, this is the acceleration error. This is the velocity error. You can say where this one is much lower, right? But more importantly, this is the measurement of the foot skidding. It measures the stability of the body. And you can see ours is much better. And this is called GP, which is ground penetration, is the foot penetrated into the ground, right? And you see this is ours is much better. The error is much lower. So you can see that by incorporating into the physics, not only using physics, not only we can reduce the amount of data, right? But also generate a much better motion accuracy in terms of physical plausibility. And this one visualize the estimate the body part forces. For example, in this body pose, right? The brighter the color is, the higher the force, right? You're going to see that this is a lot of force on you can see there's a arrow here, a lot of force on the ground reaction force. Then you also see this part has a very high forces, right? And so is this part. but the other body parts are pretty dark. That means they're not much force there, right? So this one give you a qualitative evaluation of the estimated body forces for each body part. Okay, so this basically completed this part. And let me move on. Yeah, so that's why you can see here, right? This is deformable mass model, right? So that means it's going to fit into the shape, right? Depending on the size, right? Size of the body part. So then you're going to come up with different mass and different inertia. So the equation is going to change, right? Because of these parameters are all function of the mass and the inertia.
Yeah, I have one question. So while training, you are always putting all of this symbolic data, physics based or knowledge based, all of that into the loss function.
No. This is not loss function. This is incorporated into the architecture. Put the encoder here, a decoder here, decoder. Right. This is the decoder. So right, this decoder actually numerically solve this equation. Right, it's not like the previous one we incorporate into the training function, but this one is incorporated into the architecture of the model. Okay, I can move on right to next topic. Bayesian deep learning. So this is another, so we know that modern deep learning suffer from several major limitations. One is a lack of trustworthiness, another is a poor explainability. And the root cause for this is a lacking effective method to quantify, explain, and mitigate predictive uncertainty. And we propose to use Bayesian deep learning to address these limitations. So this is a different topic, okay? So now let's say, what is the Bayesian deep learning? Okay, so first I give you a very quick introduction of a traditional conventional deep learning, right? We have a neural network, right? And the parameter of neural network are the weights. These are the weights, right? And the weights are treated as a deterministic variables. And through a training process, we'll be able to get a theta star, right? Which are the best weights for the neural network model. Then we use the theta star to perform the prediction during the testing. And the problem with this one is that we use only a point estimate theta star to do the prediction. So one side of parameter, we think that is the best parameter. And we use it to do the prediction. The problem with this is that it tends to overfit. Second, it cannot give you a good estimation of prediction uncertainty. So Bayesian deep learning is different. Bayesian deep learning treats this weight, the parameter, as random variables. They treat it as random variables. Instead of getting a point estimate, it constructs the posterior distribution of theta given d. D is the training data. And then using p theta given d to perform the prediction, not using theta star. So here, right, if we do the prediction of y given x, right? So here we are conditioned on the training data. So there are no specific theta star we can put. We put all the training data. And to calculate this term, we need to introduce the parameter of the model, theta. Then we have this integration here. As you can see that this integration basically integrated over all the possible parameters. So this means that this method uses not using one set of parameters, it uses all the parameters, right? And this term, however, is hard to calculate because the integration over the theta, right? So what we do in practice is we do sampling. We sample from the posterior distribution of theta from P theta d. We get a set of samples, theta, right? And then we compute the average over, average prediction over each sample. And we use the average prediction to produce the final result. The average prediction over multiple sets of parameters is more robust than using a single set, right? Single set. And it's also less susceptible to overfitting problems. Yes? So this is, we sample from this distribution, P theta given d. So yeah, this is a good question because this means that how we're going to construct the P theta given d. I don't have time to talk about it. Later on, we can show you, right? So we sample from here, right? So this is more robust because it's average. More importantly, because we have a multiple prediction given each input, we are able to quantify uncertainty more accurately. For example, we can compute the total uncertainty. The total uncertainty is simply the entropy of the average prediction. That gives us the total uncertainty. Then we can also compute the aleatory uncertainty. The aleatory uncertainty is the average entropy over each prediction. And the aleatory uncertainty measures the inherent noise and the perturbation in the data. So if you have high noise, high perturbation in the data, the aleatory uncertainty is high. More importantly, we can obtain the epistemic uncertainty. The epistemic uncertainty is simply the difference between the total uncertainty and the aleatory uncertainty. And the epistemic uncertainty is something that only Bayesian neural network can estimate. Epistemic uncertainty measures the model's lack of knowledge about the data. It is inversely proportional to the data density. If the data have low density in the training data, then its output will have high epistemic uncertainty. So this is the basic idea about a very quick introduction about the Bayesian deep learning. Now I'm going to show how we can use this to solve another computer vision problem, right? So here, our interest is what? We want to do complex human activity recognition, right? Using a transform. So input is a sequence of images that capture the human activity, right? Then we go through an encoder, and that encoder basically generates the tokens for every frame, right? And then we do a position encoding, remember the position of each token. Then we go through this attention mechanism to generate this attention matrix. And then this attention matrix feeds into a series of transformer encoders, finally generate the output embedding, right? Then the output embedding is fed into a softmax. We can get to the class of the input sequence. So this is the conditional deterministic transformer, right? So we introduce this probabilistic transformer or Bayesian transformer. The only change we make is this. In the attention, right? In the traditional transformer is deterministic value. For example, this is the attention between token I and token J. It's simply equal to the product of query I with the kj. That gives the Rij is the attention score, one attention score, right? But here we assume this attention score follows a distribution. We do not assume it's a deterministic. We assume it's a random variable that follows a Gaussian distribution. Then we use a neural network to estimate the mean and the standard deviation of this distribution. And then, given the distribution, we'll be able to sample it. We get multiple scores for each pair of token. Instead of one score, we got multiple scores for each pair of token. As a result, we're going to be able to generate multiple predictions, because we have for the same input sequence, we have different scores for each pair, right? We're going to have multiple outputs, and then we'll be able to average their result. So this becomes average their result, and this is much more robust than if we use the deterministic. Then we only have one. We only have one output, and also from the multiple outputs, we can compute the epistemic and aleatory uncertainty. So this is the only change we made. And this paper was published at the top computer vision conference because this is the first Bayesian transformer paper, right? Even though we only changed one parameter, we did not change many parameters. We only changed one parameter, but people never, they do not think this way, right? So now you see the result here, and you see this is the performance on two benchmark data sets, right? And compare with the state-of-art methods. You can see in terms of accuracy, we're about 2% better than the best model for both data sets, right? So this is the show you that by a simple change from the deterministic attention to probabilistic attention, we are able to get 2% improvement. And in computer vision, many benchmark data set, 2% improvement can be pretty significant. And you can publish a paper by 2% improvement. Yeah. Yeah, that's we can, right now we can, because we know this is a real number, right? This is a real number. This real number can follow any distributions. But here we just make a very strong assumption. We assume it just follow a Gaussian distribution. It works in practice. Yeah. No, we can normalize. Yeah, this is before normalization. You after normalization, right? Yeah. Okay, so the more important thing here is this. We say, okay, now we can get a better result, right? But can we leverage uncertainty? So we look at the data set. We find out that the data set, the distribution over classes is imbalanced. Some of the data, called majority classes, have a lot of data, while the minority have much fewer samples. So that means this prediction favors the majority class, right? Bias against the minority class because of the data imbalance. So now the question here, can we do something to address this data imbalance? So if we superimpose the epistemic uncertainty, we're going to find out that the minority class have high epistemic uncertainty, while the majority class have very low epistemic uncertainty, because the majority class is well represented in the training data, so it have low epistemic uncertainty. But the minority is not well represented, so that have a high epistemic uncertainty. So given this knowledge, so that means we have to treat each sample differently, because sample belong to the minority class and the sample belong to the majority class must be treated differently. So that's why we use this to train two models. One is the minority model, where we weigh each sample by a normalized epistemic uncertainty, right? The normalized epistemic uncertainty, so that this weight is going to be high for my sample from minority classes, because of the right. So as a result, this model favors minority class. And similarly, we can train another model. It's a majority class, where we use a 1 minus the normalized epistemic uncertainty. And this term is going to be high for majority class. So this model favors the majority class. And then we train another model to linearly combine them to generate the final prediction. So that's the result, okay? So now if we do this, you can see the result. And we have the green bar and the red bar, okay? The green bar is the baseline, treat every sample equally. And the red bar is the model that integration of the minority and the majority model. So here you can see, here represent the majority classes. And so for majority classes, we see marginal improvements, just marginal improvements. The fused model is marginally better than the minority, right? Than the non-fused model. But for minority here, you see the improvement is quite significant. So this means that by doing this integration of majority and minority model, not only we can significantly improve the minority class performance, but also marginally, or at least maintain the performance of majority, not at the expenses for majority class. Because of what we use the epistemic uncertainty, right? So now let me show you another thing. It's called uncertainty attribution. So what is uncertainty attribution? So the goal here is to identify the source of the uncertainty. Not only we want to quantify uncertainty, we also want to know what caused the uncertainty, right? So we want to identify the source of the uncertainty in terms, identify the region in the input that contribute the most to the output uncertainty. Which part of the input image, which pixel is contribute more to the uncertainty of the output. So we use a gradient-based approach here, right? To perform. Basically, we compute the gradient of the uncertainty with respect to each pixel of the input. And we use this gradient as a matrix of the contribution of each pixel to the output uncertainty, right? And this gradient can be easily, efficiently calculated using a backpropagation. We can backpropagate, right, from layer to layer of the uncertainty, right? And then we generate the what we call the uncertainty map. In this uncertainty map, regions with, it's kind of like a heat map, right? Region with a high temperature indicate the region that are more problematic, that contribute more to the output uncertainty. So let's look at this image. So this is a cow, right? This cow looks very normal, right? But if you look at the leg, right, you find this one has some bandage. This one looks like has some shackle here. These some normally are not associated with a normal cow, right? So if you input this image to our model, it's going to tell you this model output has a high epistemic uncertainty. Then you can say, what happened? Why? This looks normal. Then you generate the uncertainty attribution, get this uncertainty map. You find this region. It tells you these are the two regions that primarily contribute to the high epistemic uncertainty in the output. So these are the regions that we should be careful, right? Either if we want to use the classification, this region should not contribute very much to the output classification, right? So this is the, yes. Or these other tools that may be the background. There's some background here that can also cause some problems. But here yeah. So this gives us a hint. That means that when we do the classification, we should not use every pixel, treat every pixel equally. Some pixel may be reliable. Some pixel may not be reliable. Can we develop a classifier that weigh each pixel? Okay, so that's what we do here, right? This is again, right? So we generate a attention map. This attention map is 1 minus mi, the uncertainty map, right? And this attention map is going to focus on the region, the reliable region that contribute the least to the output uncertainty, right? So that means that if you look at the attention map, when we do the classification, we should focus on those pixels because they are reliable. They contribute the least to the output uncertainty. So the uncertainty map is the opposite of the attention map is the opposite of the uncertainty map, right? So this allows us to generate a mask, right? For the input image, generate a mask so that the region with reliable region have high values, while the unreliable region with low values. And then we do element-wise with the feature maps. This feature map will be generated from different filters, right? And then we have weighted. So we weigh the contribution of each pixel. So we only use the feature that get computed from reliable input pixels. And we do that, then this is the result, right? On different data sets. You can see this is our, we know this is the result without using the attention. And this is the result using attention. You can see, we see a performance improvement, but some of them is quite significant. For example, for the C10, we have quite significant improvements here, right? It's right, and this one is also almost 5% improvement. This is like 5% improvement, right? Right. This one, the average is about 3% improvement, right? So, so this tells you that we not only can use the uncertainty to weigh each sample, we can also leverage the uncertainty to weigh each pixel of the input, so that we only use a reliable pixel to perform the classification. Yes?
One more question.
Direct attention map. How do you calculate the attention map? How do you calculate the attention map? Yeah. So that's a good question. So our uncertainty map, our attention map is related directly inverse to the uncertainty map. So that it measures uncertainty. It uses uncertainty to generate the attention map so that it can only identify the region which are more reliable, contribute less to the output. So if we use this reliable region, the output uncertainty will be low. So our goal is using attention map to reduce the uncertainty of Others maybe use different metrics here. Right? So even though we all call attention map, here we are talking about attention map in the sense of minimize the uncertainty of the output. Okay, so this basically, I'm done with the second part. So the final part, okay, 10 minutes, I'm done. Okay. Causal representation learning, right? So this one is quick, okay? So we know the traditional deep learning suffer from poor generalization across domains. If you try to go from different domains, it may not perform well because of spurious correlation resulted from domain bias. Because the domain bias and then they generate the spurious correlations. So we try to resolve this issue. We combine causal modeling and the inference with feature learning to learn domain-invariant causal feature free from domain biases. So that's the idea, right? We want to. So before I talk about our causal model, first I want to introduce the domain bias. There are two types of domain bias. One is called the data bias. For example, in this image, right, the goal is to do a classification of cow. But somehow it happens that in the training data set, the background is always the pasture. So all the training image contains a background of pasture, and foreground is a cow. So if you train your model on this kind of image, there's going to be a spurious correlation between the pasture and the cow. Right? Every time the model say a pasture, they're going to say the presence of the cow. Right? So if we apply this model to another image, but this time with a different background, such as a beach, and this model is going to fail because of data bias. Okay, so this is the data bias that affects the distribution of the observation. The second is the confounder, latent confounder. So this represents the unknown factors during the data collection that affect both the distribution of the data as well distribution of the labels, right? So this is called that's why confounder, right? It's for both the label and the data, and such as demographics, style, etc. For example, if I do a facial recognition, right? Age can be a confounder. When you collect data, you did not realize that age is a latent confounder. For example, if I train the facial recognition algorithm on data set consists of primarily young people, right? Then I try to test it on another data set consists of primarily older people. It's going to fail. Because age affects not only the appearance of the facial images, but also affect the distribution of the labels. So this is one confounder that we often do not realize, which is collect data. Sometimes race can be another latent confounder, right? Demographic, the race can be another, right? And so we have to, because these two types of data biases, it lead to spurious correlations. Yes. Yeah, but the question here is a lot of the latent confounder factors unknown. Right. Of course, in this case, it's pretty simple. You say, okay, I'm going to collect people, right, of different ages. I'm going to collect people from different races, right? But there are other latent confounders we do not know, right? And those are the challenging things we do not know, right? So. Yeah. A lot of times you are limited. You are just limited to certain people from certain demographics, right? You do not have that. But a lot of time this is latent. Latent means that you do not even know, right? For example, you do the data acquisition using certain tools, certain kind of cameras, but your test image is acquired with different camera. That can also introduce problems, right? Okay, so now the question here: how are we going to address? So before I tell you how we address, I give you a very quick introduction about the causal modeling and the inference, right? So what is causal modeling? So we need to employ a structured causal model, SCM. SCM is a DAG A DAG basically means a direct acyclic graph. It consists of nodes and the links. The links capture the direct links. It captures the causal relationships. So in this is the ICM that we use, right? And the X here represent the input, and the Y here represent the output, and the Z here represent the representation of the input, right? And we divide the Z into two sides. One is the ZC, which we call it a causal representation. It directly affects the output. Then we have a ZS, which is we call the spurious representation. Spurious representation, right? And then also we model the bias. This is the data bias, and this is the data bias. This is the latent co-founder bias, right? You can see the UXY affect the Z, and we assume the bias affect the Y through ZS. So this is a major assumption we assume, right? We assume these two biases affect the Y through this node, right? Okay. So in order, if we want to eliminate the influence of this, we have to what? Remove this. We know this, right? Then we can somehow marginalize them out. Or what we do is that we have to remove these links, these dotted links, in order to remove their influence for Y, because they can reach Y from this path, right? This path. But if we remove these links, then they cannot, right? So what we can do? So this is something that's very interesting in the causal, right? When we do the causal inference, we do the interventional causal inference. For example, if we want to compute the Py given X directly, right? Py given X, then this influence, they're going to influence the Y. But if we do this interventional inference, Py given X given to ZS. So the do is an operator in causal inference. It intervenes on this node, change its value to a different value, and simultaneously remove these links. Right? Remove these links. As a result, now we have a new graph. This is called the mutilated graph. Then in this graph, the influence of this through this, influence of this for Y through this is eliminated. So we just need to calculate this term. And fortunately, given this graph, if we will apply some causal inference theory, that this probability is identifiable, which means that this probability can be computed from the observation data. So this is the key, right? We first, as ICM, then we do the interventional inference, eliminate the influence of this to the Y, right? So given this understanding, now we introduce our causal representation learning framework, right? So this is our framework. It consists of an encoder, right? This is standard encoder, right? Given X, it's going to output the ZC and the ZX, right? ZC is the causal representation, ZS is the spurious representation. And we enforce the constraint that the ZC and ZS must satisfy the ICM, the structure causal model. And then the output is we predict its discriminator. We predict Y from ZC only. Right? So this is different from the traditional encoder-decoder, right? Encoder model. The traditional, basically, you have the encoder, then this representation is used directly by the discriminator. Right? Here we said the representation must satisfy this ICM. So in order to treat this one, we need to have a loss function. So the first term of the loss function is the interventional loss, expected interventional loss. Expect intervention loss, right? Intervention loss. So this term basically need to learn the parameter for both the encoder and the discriminator. So this is the expected interventional loss, right? Then we have two additional terms. These two additional terms are used to disentangle ZC from ZS. Disentangle them, right? Disentangle them. So the first term, according to this, says that the ZC and the ZS are independent of given Y. So we have to put this constraint here. This term said ZC should be similar for Y with same label and different for Y with different label. So this is a similarity constraint. By applying this constraint, we try to disentangle these two representations, in addition to they must also satisfy this. Once we have this loss function, we can train it. Then we will have the parameter for the encoder, also the parameter for the discriminator. And then once trained, we can use the py given dc to predict, right? And the unique advantage of our method is what? It is that this model can be trained from data from a single domain. If you look at the other model generalization method, they need to train their data from data of multiple domains, but our from a single domain. So this is a single, right? And use this one if we do a empirical evaluation, right? We train this on the water birth data set. It containing both data and the latent confounder bias. And this is a within domain performance. And this is our method, right? And this is the state of the art. You can see within domain, we are not the best, but we are close, right? But cross domain, so what does the cross domain mean? For example, in this data set, the cross domain means that the model is trained on water birds, but the test on land birds. The land birds will look different from the water birds, and also the land birds will have different background from the water birds. So that means there's both bias, data bias, and the correlating confounders, right? So if you, this is our model, right? This is the best. We're about 3%, better about this best model. And this model is trained on multiple domains, and ours is from the single domain. Let me finish it. Okay, I'm almost done. Okay. So this shows that our method can achieve comparable within domain performance, but a large improvement in cross-domain performance because the feature we learn are invariant, at least the less variant across domains. Yes. This term? This term? How to calculate this term?
Yeah.
Okay. Do you remember I have this equation, right? We have this one. This is the equation. This is complicated, right? This is how we calculate this. Yeah. This is how we calculate this, right? So this one, we derived this, so we are able to calculate it. But it's complicated. So I'm not going to write. And so that's how we can do this. Question? Okay, that's it. So now I'm summary of what, So as I said, current deep learning still suffer from data inefficiency, lack of trustworthiness, poor explainability, and the lack of generalization across domains. And we introduced 3 new neural-symbolic methods to address these fundamental challenges. The first is knowledge-augmented deep learning, to leverage generic domain knowledge to significantly reduce data dependency and to improve model generalization. We show how the experiential knowledge and the scientific knowledge can be incorporated into deep learning to reduce the dependency on the training data and simultaneously improve the model generalization. Then we introduce the Bayesian deep learning to accurately quantify the model prediction uncertainty, to identify the source of uncertainty, and to improve model performance by mitigating uncertainties. So we show uncertainty quantification, uncertainty attribution, and uncertainty mitigation, right, to improve the performance. Finally, we introduce a causal representation learning method by combining the structural causal model with deep learning to improve model generalization across domains by eliminating the influence of domain bias. That's it. Thank you.
Very, very nice. So maybe we can take a few questions and then feedback. So.
Yeah.
I've seen deep learning, so inference multiple times.
Yeah, that's right. Yeah. You are right. Yeah, for Bayesian deep learning, we address the complexity is fair because we have to do multiple times. That is a problem. But we also have for other Bayesian deep learning method that only we can do it only in a single pass, right? But here I'm talking about the ensemble method, where you need a multiple set of parameters.
Then those models compromise with the model.
Yeah. If you do a single pass, you can do very fast, but then the result is not as good as the ensemble method. That's the trade-off. Yeah, the trade-off. Yes. Yes.
Any other questions?
Yeah.
I had a question when you talked about the Bayesian deep learning. So you said that attention is a Gaussian variable, but distributions require a lot of data in order to get.
No. This is we just predicted this, right? We just predicted this, right? You can see we here, right? Here, right? So we just train the model. We predict the output is basically we predict the mean and the standard deviation for each pair of each pair of tokens. So in other words, we have a probabilistical attention matrix. Previously, it's a deterministic attention matrix, right? Now become probabilistical attention matrix. We assume the attention score is independent. We predict the mean and the standard deviation for each pair of token attention score.
Yeah, I think we can. Any more questions? Looks like we don't have any more questions. So again, Professor J, during pizza time, we can have conversation on this.
Yeah. Feel free to ask. Yeah, I think yeah.
One thing I want to point out, we are from IEEE. So Farid, thank you for bringing your students here from.
Yeah, we appreciate IEEE's computational intelligence. Stuff like this. Big round of applause to them. Thank you.
And John Cole is our secretary for Computational Intelligence Society. Again, you can email us. You saw that in the flyer. So if you think there are some nice talks you want to have here, like Professor G's talk, this is by the way very useful. I did not know this area, so that well we use attention mechanism, but now I'm going to change to. A lot of these things are helpful in especially industrial applications, because I'm in the medical field. I see the value immediately. So this is. Thank you very much.
Yeah, have some pizza, have some drinks.
Yeah. Thank you.
Okay.
Nice. Some more questions. I'll ask you later.
Yeah, you can. Can we turn off this?
Yeah.